This is the CSIG weekly call on AI, and I'm going to hand over to Tom Parnell to speak about machine learning in a snap.
I'm sorry, let me.
That's you, yes.
Do you see this in full screen?
Oh, it looks very clear to me. It looks full to me. I mean, it's full enough for me. So yeah, please. Oh, you're making it fuller. But now we only see a portion.
Now it's better.
Okay, go. Please proceed.
Great. Hi everyone. I'm Tom Parnell. I work in the IBM Research Lab here in Zurich in Switzerland. My research interests are machine learning as well as information theory. As well as doing research here in the lab, we're also actively involved in a number of IBM product development, in particular IBM Power AI and also IBM Flash System. So today I'm going to talk about our machine learning work, in particular a new library for machine learning called snap-ml, which was initially a research project we started here with PhD students in the lab here, which over 2-3 years has matured into now product level. So snap-ml is part of Power AI since now a few months. So it's available and free to try on IBM Power System. So how do I go to the next slide? There. So before I get into what snap-ml is, I'd like to introduce the kind of problems that we're trying to solve. So snap-ml focuses on a fairly general class of models called generalized linear models. This includes regression models like ridge regression and lasso regression. This is where you're trying to predict something like a stock volatility, some analog value. But the sorry, I just need to close that. But generalized linear models also encompasses models which are used for classification. So that is where you have a number of classes and you want to try to predict which class belongs to which feature vector. So an example of this would be something we're going to see later in this presentation, which is predicting whether a user will click on an advert or not. So two very widely used models for classification are support vector machine and logistic regression.
So Tom, I just wanted to say, you know, your slide is still the first slide.
It is?
Yeah.
It's not on my...
Okay, well, maybe you want to restart. Okay, now it's moved. Now it's moving. So we never saw the slide before.
Okay, this is the slide I was talking about here.
Okay, great. Okay, good. What are GLMs? Okay.
Okay, good. Yeah, so sorry, let me then back up a bit on this slide. So GLMs are generalized linear models, which includes models for regression, such as ridge regression and lasso regression, and also classification. And classification models that we support includes support vector machines and logistic regression. So logistic regression is a bit of a confusing name. It is technically a regression, but the vast majority of people kind of threshold the output to use it for classification. Logistic regression is also widely used in the field of deep neural networks, where it's often known as the softmax layer, which is normally the final layer in a neural network used for classification. So why are GLMs useful? One of the main reasons GLMs are used is when you have really enormous data sets. So we're not talking about data sets with a few million examples or million features. But when you have terabytes and terabytes of data, where you have billions of training examples or billions of features, that's when it's very hard to scale more complex models, and you want to look at the models which fall within this family, GLM. So another nice thing about generalized linear models is that while for in the field of deep learning, where you have a non-convex optimization problem, the state of the art there is to use some variant of an algorithm known as stochastic gradient descent. One of the challenges there is that that algorithm needs a lot of tuning. You need to tune what's known as the learning rate. Whereas for GLMs in the last few years, there was quite some research into finding better ways to train them, which don't involve such a parameter. So there exist algorithms that need much less tuning to train these models. Thirdly, another nice thing about generalized linear models is they're very easy to interpret. So what that means is when we use a GLM to make a prediction, we can also go back and say, why did the model make this prediction? We can identify the important features which resulted in the model coming to the decision that it did. And this topic is obviously of significant importance in Europe, where we have this new data protection regulation, which gives European citizens some rights when it comes to contesting the decisions of algorithms, and some degree of a right to some rationale behind the decisions which machine learning algorithms came to. So finally, we see that generalized linear models are still very widely used in industry and in practice. So in this Kaggle State of Data Science survey from last year, they asked around 16 data scientists and machine learning practitioners which algorithms they're using. And actually logistic regression was the most popular model in that survey. So around 64% of people say that they're using. So now to talk about snap machine learning. So would like to clarify on this slide what snap machine learning is and what it is not. So if we consider the machine learning field broadly, this is a very general descriptor. This encompasses both deep learning, that is using neural networks with many, many layers, as well as generalized linear models. But these are distinct, apart from some small overlap, as I mentioned before with the last layer, they're distinct fields. So snap-ml does not do deep learning. We focus only on generalized linear models for now. So when our design goals for this project were to target that class of models, that family of models, try to train them in the fastest way we possibly can. And for that, we looked at the machine learning frameworks that exist and are widely used, and we tried to see, okay, what are their advantages, what are their weaknesses, and we identified 3 key areas. So those areas are GPU acceleration, distributed training, so that means scaling out to more than one machine, as well as supporting sparse data sets. Now, this is very important for GLMs. There are many applications, like, as I mentioned before, click-through prediction, as well as financial applications, where we have data that's nothing like images, which is used in deep learning very often. We have a highly sparse data set. So this is a very important feature, especially for GLM. So when we look at what's out there, we have scikit-learn, which is a Python framework for machine learning. It doesn't really do deep learning. It doesn't have any GPU acceleration. It doesn't do distributed training, but it does have excellent support for sparse data. We also consider the machine learning framework from the Apache Spark project, that's ML-lib. Again, this has a similar set of algorithms and functionality to scikit-learn, but again, it doesn't have GPU acceleration. On the other hand, it does natively support distributed training because it's built on top of Apache Spark, which is a distributed data processing platform. And it does have decent sparse data support. Thirdly, TensorFlow is actually a more general framework than the other two. It's a framework for expressing computation on a graph, but its primary use is for machine learning, both linear machine learning, GLMs, as well as deep learning. It does have GPU acceleration kind of seamlessly built in. It does have some distributed functionalities, a bit harder to use than Spark, but it is there. And its main weakness is that it doesn't support these kind of sparse data sets very well. So with snap-ml, we focus on this class of algorithms and try to excel in these three areas. So the architecture looks like this. How we get very fast training is by exploiting parallelism in modern heterogeneous computing infrastructures. And we do that by considering three different levels of parallelism. So in the first level, we consider a cluster of machines. So that is a number of worker nodes. These may be servers, they may be workstations, but they communicate with each other over some network interface. The second level of parallelism is within one of those workers. So within a server, we may have a number of CPUs, say 2 in this example, as well as a number of accelerators like GPUs. And these GPUs are very often connected with each other using some very high-speed interconnect. So that is an interconnect like NVLink or NVLink 2, which is much faster than the network interface itself. And finally, within each CPU or within each GPU, we consider the parallelism across the computing cores which are available on that accelerator. So we develop new algorithms to effectively map the training of these models onto that massively parallel hardware. So we'll cover that a bit later. So yeah, this slide describes the GPU acceleration in a bit more detail. So as I mentioned before, the state of the art for training linear models is not to use stochastic gradient descent, which is the state of the art for deep learning, but rather a new algorithm, which was, it's an old algorithm actually, but its nice properties for training GLMs was discovered in around 2013, and it's called stochastic coordinate descent. So we were following these developments and saw a number of papers in the literature where people tried to map this algorithm, stochastic coordinate descent, onto multi-core CPUs. But we saw an opportunity there because no one had considered how one might map this thing onto a massively parallel GPU. And it's not that simple because the algorithm is not inherently parallel. It's a very sequential procedure. So we had to develop some asynchronous tricks to make this work on the GPU. And that's an algorithm which we published in a journal earlier this year in this paper, Terabyte-scale coordinate descent on GPUs. And the idea is that we map one thread block to process every coordinate in the model and distribute these thread blocks across the whole computing power of the GPU. And we show in the paper that we're able to beat the state of the art, which uses many cores, by at least 10x. So another key aspect of how we get snap-ml to train fast is how we feed the GPU with data. So snap-ml, as you saw a few slides ago, can scale out. So we can use more than one server to do our training. We can use more than one GPU. So if we have a big data set, one option is that we just throw more and more servers into the cluster until we have enough memory, enough GPU memory to fit that data entirely in the GPU memory. But this is not always an option. Maybe you have a fixed infrastructure, maybe you have a fixed cloud budget. So it's very often the case that the data set is so big that it does not fit in your GPU memory. So in that case, what we need to do is to batch the data. So you need to split the data set into smaller chunks, which can fit in the GPU memory. And then we partition the GPU memory into one area, which is a copy buffer, and the other area is the active memory region which the GPU is training on. And we leverage some of the features provided in the NVIDIA CUDA toolkit to pipeline the GPU training. So what that means is the GPU, in any given time, the GPU is training on the current chunk of data, while at the same time we're copying asynchronously the next chunk of data into the GPU memory. And what we find is that this always helps you. It always hides some of that copy time. But the cool thing is when we use like Power 9 servers, which have very high speed interconnects like this NVLink, we can completely hide that copy time behind the training time, which means we can get almost full utilization of the GPU. So we see them working almost at 100%, and they're never idle waiting for the next piece of data to come in. So in terms of the software and how Snap Machine Learning is packaged, it looks something like this. We have an underlying C++ CUDA library. This is where the algorithms themselves are implemented. But this is something which is never exposed to the end user. So today there are three different ways to use SnapML. There's a SnapML local. So this is a single node deployment of SnapML. Therefore, it can be used for small to medium scale data, but it can't train on data which is too big to fit in the CPU attached memory of a single server. However, it does support multi-GPUs. So if you have 4 GPUs in your server, SnapML local can utilize all of them. And it's exposed to the user with a Python API, which is compatible with scikit-learn. And I'll show you an example of that later. If you have some scikit-learn application, which is using GLMs, you just have to change 2 lines of code in order to use SnapML and benefit from the GPU acceleration, which is offered there. Now, if you have a big data set, there are 2 options for how to train it, how to utilize SnapML to train that big data. One is to use the MPI interface. So this is MPI is a distributed programming framework, which is able to utilize very high performance hardware like InfiniBand, things like that. So it's very well suited to HPC-like environments where you have very high-end hardware. So this obviously can scale to as many GPUs as you have in the cluster. But one of the cool things here is MPI is normally, people think of it like I need to write C++, I need to do compilation, I need to link against the libraries. You don't have to do that with snap-ml-mpi. We have a Python API, which is as easy to use as scikit-learn, and I'll show you an example of that shortly. Finally, if you have an Apache Spark environment, so you can use our Spark API. This supports obviously Python, Scala, and Java, the native languages of Spark. It is similar in functionality to the MPI, but typically is a bit lower performance because we see many overheads associated with the Spark framework. So yeah, as I mentioned, this is an example of how to use SnapML local. That in the beginning, the message we want to give with this slide is that you can use SnapML local with sklearn. So you can use all of the auxiliary functionality from sklearn, like loading data, pre-processing, evaluating, using the metrics from sklearn. The only thing you have to do is to import, in this example, import a different logistic regression object, tell it which GPUs to run on, and that's it. So aside from that, all of the rest of the code is the same. In terms of the MPI code, now the interface is very similar to scikit-learn, but it's not exactly the same because scikit-learn is not a distributed framework. So we have to re-implement some stuff like data loading and metrics. It's all done in snap-ml-mpi in a distributed way. But in the sense, the interface is extremely similar. So you describe your application in high-level Python code. You tell it how many GPUs it should use on each node on which it will run. And then you launch the application using the MPI run program. So you give it a rank file which says which hosts it should run on, and then you just run the Python. So it's relatively easy to use despite using very high performance MPI backend. So just want to show you some results now. We have about 10 minutes left. That's good. I'll try to get through this so we can have some questions at the end. So the application we consider here is click-through rate prediction. So that's whether a user we try to predict whether or not a user will click on a given advert. This is still the core business of companies like Google, Facebook, and it's a cool application for GLMs because you have huge data. You have labeled training examples which are being generated more or less in real time. So you have never-ending amounts of data. So for the study, we consider two data sets. So one it's a data set released by Criteo for a Kaggle competition. So it has about 4 million training examples and it's around 40 gigabytes. We also consider another data set released by Criteo, but this is one of the largest publicly available data sets tool. It has 4.2 billion training examples, and it's around 3 terabytes in a widely used format for such data set. So first, we look at the single node performance on the smaller data set, on the Kaggle competition. So we compare, we use a Power 9 server for this analysis, and we use a single V100 NVIDIA GPU. And we compare scikit-learn and TensorFlow and SnapML. So on the x-axis is the training time, and on the y-axis is the logistic loss, which you can think of like a measure of accuracy on the test set, so on the holdout data. So scikit-learn can't use any GPU, it doesn't have that functionality, but it does have a very efficient C++ implementation of logistic regression is the algorithm here. TensorFlow we see is actually slower than scikit-learn, even though it can use a GPU. This we attribute to TensorFlow not having good support for sparse data, and this data set is very sparse. So SnapML, on the other hand, can use the GPU, and it deals well with sparse data. So we see it brings an acceleration of about 10x over scikit-learn, and even more over TensorFlow in this example. Then for the huge data set, we searched around and found all of the published or reported results which people have achieved on this data set. This figure summarizes all of those results. So on the x-axis is the training time in minutes, and on the y-axis is the logistic loss or accuracy. And so we see a bunch of different results using different frameworks, using different hardware. So the best in terms of kind of trade-off between timing and accuracy that we found to date is this yellow point here, which is actually a result reported by Google on their cloud platform. So they used around 90 machines, instances in total, and they train a logistic regression model on this huge data set in around 70 minutes, and they report this particular log loss. So Google also mentioned in their blog post that they don't find GPUs speed up this application in TensorFlow, which is confirmation of the result which we saw on the last slide. So when we compare snap-ml with this, we can train this huge data set using 16 V100s. That's our 4 Power 9 servers. We can train it in around 1.5 minutes, and that time includes loading the data from SSDs and all of the iterations of the training itself. So we get slightly better accuracy in more than an order of magnitude faster training time. So that's basically it. We have 5 minutes for questions. So just to summarize, snap-ml is a new framework for very fast training of generalized linear models. It can benefit great from GPUs, it can scale out to many nodes, and it can benefit from very high performance hardware like NVLink, which is present in Power 9 servers. So snap-ml is publicly available. You can download IBM Power AI from version 5.2 onwards and try it out on any IBM Power system. So thank you, and I'll be happy to take any questions which people may have.
Svetlana has a couple of questions. I think I unmuted you, Svetlana, if you want to go ahead and ask.
Thank you, Susan. Can you hear me?
Yes.
Okay. Yeah, so I had a few questions. Okay, so this is only specific to Power, so you cannot use your code on other platforms, is that right?
It's a good question. So right now, snap-ml is only offered as part of Power AI, which runs on Power platforms, yes. From the technical perspective, snap-ml can benefit from lots of the great things we have in Power systems, like NVLink 2, but there's no technical restriction why it can't run on other platforms. However, it's not offered for those platforms today. I hope that answers your question. I have to be politically correct in answering that.
I think, yeah, you have C++ code there, so if you wanted to use it elsewhere, then we would need to port it, right?
Yes, it needs to be obviously compiled, and we need to build artifacts for, say, x86. But that's not offered today, but it can be. I would like to see that in the future, personally. But
yeah, I think it would be nice to be able to add it, but the problem is that not all computers have GPUs, so it may be difficult, I guess. Okay, do you export PMML?
PML is a format for models, is that right?
Yes, for model deployment.
Tom, you're speaking to IBM's representative of PMML models in the data mining organization.
Okay, great. No, that's not something we do today. It's definitely something we'd like to think about.
Yes, please. It would be good to let me know if I could help with that.
Sure, maybe we can take that offline a bit. I'd like to know more about that and what it would take for us to support that. That would be really cool, actually.
Okay, great. Thank you. Let's work on that.
Any more questions for Tom? And please thank Tom in the chat for his great talk. Any more questions?
Tom, can we get your paper, please?
Sure, yeah.
And the slides?
The slides are already out there, Svetlana, every week.
Great, thank you.
And the recording, always.
Yeah, I can follow up with you with the paper afterwards. I'll send you a mail.
Great, thank you very much. It's very interesting how you do it. Yeah.
Okay, thank you.
It's great.
Anyone else? Okay, well, thank you very much. Next week, I think we have a talk on making correspondences. And thank you very much, Tom. And thank you, everyone, for your attention. And I'll be posting the recording a bit later today.
Great, thank you.
Thank you.
Thank you.
Thank you. Bye-bye. Bye.
Thank you.